All right, let's look at vector space. Right. So vector space is sort of a generalized version of a space like Euclidean space that we're familiar with, where you have vectors with three components, x coordinate, y coordinate, and z coordinate. And the vectors interact with other vectors in a certain way, or you can do scalar multiplication in a certain way. And we want to kind of extract the essence of such a space. Right? So here's the definition of a vector space. Right? So we say, V is just a non-empty set along with two operations, addition. Right. So this notation is the notation I made up since I don't want to write this, spell out scalar multiplication every time. So it's f times. So this is my notation for a scalar multiplication. So you have a non-empty set with addition and a scalar multiplication, and it is called a vector space if. All right, so non-empty, we got that. And for all scalars, or the A and B from a field, and three vectors, v, w, and y, right? Following rules, right? So it has to be closed under addition, right? If you add vectors up, you should stay in that set. And also it has to be closed under scalar multiplication. So if you multiply by a scalar, vectors should stay in that space, right? And the next one is associative, right? So you have v plus w plus y. You can add up v and w first, or you can add up w and y first. Doesn't make any difference. And also, vector addition has to be commutative. You can add v plus w or w plus v. Exactly the same thing. And you should have additive identity. If you add the identity to any vector, it's not going to do anything, right? And we should have additive inverse, which is negative v. If you add that to v, you're going to get the additive identity. All right. And the scalar multiple have only a couple of rules, and which is associative, right? You can multiply AV first, then apply that to V, or you can apply B to V first, and then apply A, right? And identity, you should have an element identity 1. If you multiply a vector by 1, you should get exactly the same vector. All right, so this is a multiplicative identity. All right, and a couple of distributive rules. You can distribute a scalar multiple to vectors to each term. So if you have A times quantity V times W, then it's the same thing as AV plus AW. All right, and we can also distribute the vector, to scalars. So you have quantity A plus B times V, then you can basically distribute V to A and B, so you have AV plus BV, right? So those are the rules for vector space. So once you have a non-empty set with addition and a scalar multiplication, satisfying all these rules is called a vector space. And certainly the Euclidean space, will satisfy all these conditions. All right, that's it. I hope that this was clear.